Okay. So, oh, fuck. Okay, it's back. Okay.
What an epic start. I love it.
Yeah, so talking about like what cryptography is used for. Oh, maybe I can write on the thing. So you start with like your alphabet, you know, you got, okay. Okay.
You got it, look.
What? A, B, C, D, and so on. If you want to talk about Caesar cipher, that's like the basic, like most simple thing you can do. It's been around, yeah, no, it's sort of. It's been around since like, you know, Julius Caesar. That's the idea, like the Romans. You basically just add 1. So if you want to write the word, okay, wait. So this is Z, A, B, C. So if you want to write like a specific word, like, what's a word you can write? You can't write anything with these letters. Wait, actually, let's write dab. Okay. So we're trying to write dab, but we want to do some sort of like change to make it so that people reading it don't know that it's actually the word dab. So we take D, it goes to C, so we write C, A, Z, and B is A. So instead of writing dab, we write Z, and nobody knows that it's actually the word dab, but if you know that you actually just found it by adding 1 to the letter, you can actually go back by subtracting 1, and you just basically do everything in reverse, and you get dab. So that's like basically the simplest sort of thing. But you can actually take this and do even bigger things. So say, oh, okay. You need to press. Oh yeah, you need to erase things. Yes. Okay. Okay. So yeah. So what if instead of just having like a single key, you have like an expansive key? So like your first one is like 1. Your other one is 2, and then your last one is 1 again. So this would be for like encrypting larger lengths of text. So like seeing how it works on a very small scale is kind of tricky. But you do the same idea where like you write out like the whole alphabet, you shift everything by 1, and so that's your first like shift. Then your second thing, you want to shift it by 2, so you take the whole alphabet, and instead of A, B, C, you write C, D, E, and so on. And then for the third letter, you actually go back and use the same alphabet as you used for the first one. So like, hello. So if you have like A, B, C plus 1 goes to B, C, D, and A, B, C plus 2 goes to B, C, D. Oh fuck. Not B, C, D.
Alphabet is hard.
Yeah, exactly. C, D, E. And then you have this as like your key. So if you want to write the word cat, or no, let's write dab again, because we just want to use these. What if we were to, yeah, okay, dab. We're trying to write dab encrypted with 1, 2, 1. So we go and we say, okay, what is D over here? It's E. So yeah, maybe we'll just extend that. And then A is C, and B is C. So dab is now ek. And you can do this for like an arbitrary length of like key, if you want to extend it even farther, or if you want to just like keep it short to like, say you want to remember the key and you want to be able to tell someone very quickly, so you can actually use like another word. So like say the word that you want to use is cat, and you encrypt everything over cat. You can do this because you know that this is like, so if we were to assign values to each letter, A would be 0, B would be 1, C would be 2, and D would be 3. So this actually becomes 2, 0, and then whatever the number is that goes with T. I don't know it. But yeah, so if it would be like the same way that you're using 1, 2, 1 here, but you can just use a different like pattern or sequence of numbers. And so this actually is a really good way to like encrypt things, and it stuck around for several hundred years. And then like came around like World War II era, they decided like they could use some other stuff. So like for example, the Germans, they had a very good computer that they could use to like encrypt their messages called Enigma. But even that can be broken, as was seen with Alan Turing. So we come to modern encryption, and this is the really cool stuff that they can say is actually like provably difficult to decrypt. But there are still some things that like could potentially decrypt stuff. For example, if you have a quantum computer, you can actually find an algorithm that will like that's going to factor large primes. And since a lot of like the modern encryption schemes are based on multiplying like large primes together, then if you want to like factor that number, you can't do it using like traditional methods, but using a quantum computer, there's like an easy way to do it. But that's not really the stuff that we're going to be talking about in this class, because today we're going to be talking about multiparty computation. So what that is just, say you have some sort of thing you want to evaluate. If it's, for example, a vote, you want to add up all the decisions of each person that is in the vote. So each person says yes or no, 0 or 1, and you just want to add them up across the whole room. But you don't want each person to actually publicly say what their decision is, because it's supposed to be a private thing, so that they're not able to like be biased by the other votes of the other people, or feel like they're going to be like persecuted or something. So it's the sort of thing where you actually don't gain any information about the other people's decisions or inputs, and the only information you get is the output of the entire computation. So that's like secret stuff. And then there's another cool thing called secret sharing, where say you've got like a secret like formula, or no, okay, you can actually use it in a more real world situation like nuclear warheads. So if you have these nuclear warhead locations, these coordinates, and you want them to be able to be accessed by like a country at only a certain time, like when all the people come to this decision that they're to be accessed. However, you don't want that decision to lie in any one particular person's hands. So you find a way to encrypt the information so that only by having a certain threshold number of people working together, they can gain the information. And the idea is that if you have any number of people up to that threshold working together, they can gain no information about the secret, but once you reach the threshold, you get all the information. So that's like a cool thing. If you want me to talk about like how to do this in practice later, I can talk about it. Just up to you guys. But yeah, we're gonna get into like some more, maybe not necessarily interesting stuff, but more specific stuff. Starting with symmetric key encryption. So that's what I like basically just told you about with like the Caesar cipher. So you have Alice and Bob. These are like your two parties that are trying to do this encryption. And they agree on a very secret key. That key can be anything. It can just be a number. It can be the word cat. It can be a sequence of like zeros and ones in binary. And so here we have Alice, who uses the key to encrypt their secret message. Some sort of encryption scheme. We don't really care what it is. This is just like the process. It can be like Visionaire, where you have like a long like string, or it could just be one number. We're not sure. Okay, so Bob also has access to this key because they agreed on it before this process even began, so that when Alice sends the encrypted message to Bob, Bob can use the key to decrypt the message. So he basically gets the information that Alice was trying to keep secret, so that anyone who doesn't have the key is not able to understand the information, but because Bob does have the key, he can understand it. So this is made possible by like certain things, certain like properties of functions that can go like really easily in one direction, but are pretty hard to do when in doubt, like in the reverse, without like some secret information. And then Yeah, so Eve intercepts the message. Eve is an eavesdropper. And Eve just sort of looks at it. She